Hello everybody, I am Jing, and today I'll be sharing with you about my final year project titled Remote Sensing and Verification of Forest Growth in Singapore. Have you ever wondered what satellite images can be used for? In recent years, the advancement in the technology of remote sensing has enabled us to use satellite images for a variety of purposes such as weather detection, city planning, and many more. This project made use of Sentinel-2 images provided by the European Space Agency and various remote sensing techniques to analyze vegetation changes in Singapore from 2016 to 2021. Rapid urbanization has brought about an increasing population and number of buildings in cities. Research has found that between 1953 and 2018, Singapore lost nearly 90% of its mangroves to urban expansion and other human activities. However, trees play an important role in creating a livable environment as they provide many benefits such as helping to mitigate the urban heat island effect and climate change. To study how the green landscape has changed in Singapore, this project hopes to first provide an easy and accurate way for relevant authorities to map the land use of Singapore through publicly available datasets. Next, by studying the effects of vegetation growth and how land use has changed in Singapore, this study then hopes to provide valuable inputs to authorities, which may be able to help them better evaluate their positions when it comes to tree reforestation or deforestation. This will also aid them in improving policies involving green spaces in Singapore. This project has been split into three parts. In the first part, tree cloud removal methods were explored and compared as a step to pre-process the satellite images. In the second part, tree change detection methods were adopted and compared to analyze vegetation changes in Singapore. In the last part, the effects of vegetation change on the temperatures of certain areas in Singapore were then investigated. I'll now give an overview of the first part of the project. Satellite images obtained usually include cloud and cloud shadows, which makes extracting information from satellite imagery much more difficult. As such, the detection and removal of clouds and shadows from satellite images are important pre-processing steps. The project explored three different algorithms, namely QA60, Cloudless, and FMask. The QA60 is an embedded cloud mask layer in the Sentinel-2 Level 1C and 2A products. The mask enables cloudy and cloud-free pixels to be identified. Processing is performed with data sampled at 60-meter spatial resolution for all spectral bands. Cloudless is a single-scene cloud detection algorithm that works on a global scale and uses machine learning techniques. Cloudless uses pixel-based classification, where it assigns each image pixel a probability being covered with a cloud solely based on the satellite spectral response for that pixel. FMask, which stands for Function of Mask, works for Landsat 4 to 7, 8, and Sentinel-2 images. The original FMask algorithm, developed in 2012, only worked for Landsat 4 to 7 datasets. However, subsequent improvements were made and the algorithm expanded to cover Landsat 8 and Sentinel-2 as well. Experiments of cloud removal using the various algorithms were done over a one-year period from 1st January to 31st December 2021. Based on the experiments conducted, the project was able to provide a summarized conclusion of the advantages and limitations of each algorithm, as shown in the table. In conclusion, Cloudless will be the most ideal pre-processing method to use if we are using Sentinel-2 datasets for analysis. On the other hand, if you are using Landsat 8 datasets, FMask will be a better choice due to its higher accuracy and ease of use. In the second part of the project, tree change detection methods were used and compared, namely image differencing, post-classification comparison, and a combination method of the two. Image differencing is an unsupervised change detection method which is performed by subtracting the digital number value of a pixel in one date for a given band from the digital number value of the same pixel for the same band of another date. Through the image differencing method, areas with significant vegetation change, for example, deforestation or reforestation, can be easily identified. Some of these areas include some parts of the Western Water Catchment Area, the Tengah Forest, the Mandai area, and some parts of Punggol, as shown by the figure. The post-classification comparison is a popular quantitative method of change detection. It first requires the satellite images to be classified into land use maps. The two maps are then compared on a pixel-by-pixel basis using a change detection matrix. The change detection matrix provides information about how classes have changed. The accuracy of this method depends highly on the quality of the land use maps. Thus, this project also explored various algorithms and hoped to come up with an easy way to accurately map the land use of Singapore using Sentinel-2 datasets. The general pipeline to create a land use classification map is shown by the figure. The project experimented with a novel object-based classification approach which combines the SNIC and GLCM algorithm. This method was compared to the traditional pixel-based approach. The SNIC algorithm is an image segmentation algorithm which was developed based on the simple linear iterative clustering algorithm used to group pixels into objects, and the GLCM algorithm is used to calculate textual indices based on the clusters obtained from the SNIC algorithm to improve on the land use classification. The experiments found the object-based approach to be more accurate with an accuracy of 85.1%. The land use classification map obtained is shown by the figure, and the areas of change formed by the method is highlighted by red in this figure. Moving on to the last method, the pipeline of the combination method is as follows. Instead of applying the post-classification comparison method to the whole of Singapore, the combination method will only focus on areas with significant change identified by the image differencing method. In the combination method, the change areas identified in image differencing are first encoded into a binary mask which signifies change or no change. The binary mask is then overlaid onto the two classification maps produced in the post-classification comparison method, and only those pixels that were detected as having changed are analyzed. The changes identified by the combination method are shown in the table. The project also summarized the advantages and limitations of each change detection method as shown in the table. Moving on to the final part of the project, a well-known benefit of vegetation is that it improves the urban environment by helping to reduce ambient temperatures by transpiring and providing shade. Thus, it is hypothesized that higher greenery leads to lower temperatures. To determine whether vegetation really helps to reduce temperatures in Singapore, areas where there's vegetation lawn and gain were explored, and how temperatures have changed over the years in those areas were investigated in the last part of this project. Due to time constraints, only preliminary time series analyses were conducted, and this part of the project will be further expanded on in future works. In conclusion, this project found that the S2 method is the most suitable cloud removal algorithm given its greater ease of use over the F-mask and better accuracy in identifying cloud covers as compared to the QA60 band method. Additionally, this project found an easy and accurate way to classify land use using only publicly available datasets with the SNIC and GLCM algorithms, where it was concluded that the combination of the two algorithms helped to provide an improved accuracy of the classifier. Finally, the change detection methods adopted found significant vegetation changes in areas such as the Western Water Catchment Area, Punggol, Changi, and Mandai from 2016 to 2021. Thank you.